to record it. And let us see. Now I'm sharing the screen. Do you get this? You got it now?
Sir.
Yes,
Sir.
Now, okay, this is the come. So this is also visible. Okay. Yes or no? You respond.
sir.
Otherwise, I cannot proceed.
Yes, sir.
Now, now I think you know the trick of carbohydrate chemistry. Carbohydrate is quite simple molecule. The molecules are quite simple, but it is little bit different from other. They keep on changing their character. As a result, they keep on their behavior also changes. Today's alpha D plus glucose I need not write. I assume that everybody know it now. So conformational structure, actually that is the real structure of the molecule. So we must know, because all the properties that are exhibited by the molecule is because of its structure. So that structure should be properly understood and it should be known. Already we have, it comes from that cyclohexane structure, and because we take this one, say, monosubstituted cyclohexane, we know that one axial bond gets converted into equatorial and equatorial to axial. We know that one. But equatorial substituent is more stable than axial substituent. That also you know very much from your stereochemistry, that first semester class. Then 1,2-dimethyl cyclohexane, when we take, it can be exist and cis and trans. In trans form, it is either AA form or EE form. But EE form will be more stable, so that will be the what is called this. In this form, if it is trans, that means EE form, it will exist in EE form. And if it is cis, it should be, one should be axial position, another should be equatorial. So that is also we know. And so if we come to now glucose molecule, glucose exists in two anomeric forms. These are called anomers. You know, by now you are sure what is that anomer. This OH group that we find here is different from other OH group. Other OH groups simply they behave like an alcohol. But this OH group is also alcohol. At the same time, it is also an aldehyde. Yes or no? Huh? This is not the same alcohol that we get. Huh? Because this is also OH group in one position in the cyclic form, but in the, that means that time it will behave as an alcohol, but is also converted into that that open chain form, which is an aldehyde group. So this is a very unique character of this type of molecule. It is aldehyde. It behaves as an aldehyde group in one solution, also in some reactions, but it's also an and this OH group is your anomeric OH group, is an hemiacetal structure, hemiacetal OH group. All hemiacetal will have one OH group, you know that one. And because this new chiral center is created, so we'll be having both alpha and beta. Already alpha glucose, I asked you to write it down. You remember like this. This is right, left, right, and then other things will be. And for alpha, this OH group will be on the right hand side, alpha. So right hand side goes down, dia down, and the beta will be up. That's all. Now, when we convert it into conformational structure, we have to just look into the adjacent two OH group. These two adjacent OH group in Howard projection, you just see in the projection, they are in trans. So this should be trans. Trans means what we have seen, it is E. So both will be in E. Then we go to the next one, 2, 3. 2, 3, the OH group are also trans. So they also should be, this is already equatorial. So this should be equatorial. And also 3, 4, this will be, they are also trans, so this should go also equatorial and equatorial. That's all. So another here, carbon number 5 here, that is bonded to CH2OH group. This is given in the, it is kept in the equatorial position because that is a bulkier group, not in the axial position. So that way, so when we go to beta alpha, these are going to be, these two OH groups, C1 and C2, they are going to be in the C's. So obviously this will go to the axial position. So that is the difference between alpha glucose and beta glucose. In alpha glucose, this OH group, all the OH group will be in the equatorial, including the anomeric OH group. When it is, that will be beta. When it is alpha, it is in the axial position. That is the difference. So with that, we come to our today's class. That already the note has been passed on to you. So we'll discuss and we can go comfortably. I mean, we can go fast. Now, what is written here? Other monosaccharides. Okay, some other monosaccharides. Let us come to fructose structure. The fructose structure, I am not elucidating fructose structure. That is, you can read from the book. It will be done in the same way that is there. But fructose is found to exist in as 5-membered ring form. So fructose becomes a furanose ring. The open chain structure of glucose and fructose are similar in the sense that the aldehyde group becomes ketonic group, so it comes to the C2, and then C1 becomes CH2OH, and the other 3 OH groups remain same in the as glucose. So left, right, right. So that is the open chain structure. Like glucose, this also become ring structure. So what will happen? This lone pair will interact with the carbonyl group and then go to this position, and then so a new carbon atom chiral center is created here at C1 in sorry, it's C2 in this case in both this molecule. So what will happen? The OH group that is formed can be there in the right hand position or in the left hand position in the Fischer projection. This is the Fischer projection. So what will be the name for this one? This is going to be your alpha D fructofuranose. That is the complete name. Because once we write furanose, that means the ring size is also mentioned. In case of glucose, that becomes pyranose. So alpha D minus. It is minus because it is liver rotatory. It's not extra-rotatory. Fructofuranose. And this will be your beta, the OH group on the left-hand side, beta, bia. So that all these things are here. Now, when we convert it to Fischer projection, sorry, Howard projection, what is the same way we have to consider? The group on the right-hand side go down, group on the left-hand side go up. But here, this the ring carbon atom, this becomes the anomeric carbon atom is carbon number 2, not 1. In case of glucose, it was anomeric carbon was 1. Here it is carbon number 2. So the carbon number 1 is CH2OH. Just this is on the right hand side, this goes down. This is your C2 here. So the OH group will be up. Then comes carbon number 3. This is 3. So this will be your, this OH group is up. Then carbon number 4, OH group is down. Then this is C5. C5 I should have given also number here. Anyway, that is understood. C5 is bonded to CH2OH, so that goes up, and also carbon number 2. So through this oxygen breach, that is, so that becomes the, what it is? It is your beta. And always remember in our projection, beta OH group, anomeric OH group is on the top. And this will be alpha. The difference between alpha and beta will be in this OH group, anomeric OH group. Got it or not?
Yes, sir.
Yes,
Okay.
sir.
Okay. Now here, this is another for galactose. Now if we go to galactose structure, suppose Galactose and glucose, what is the difference? The difference is only in the carbon number 4. In glucose carbon number 4, the OH group is down, here a OH group is up. So it is D plus galactose. Remember, this is dextrorotatory plus galactose. And this is the aldehyde group. Same way, the C5OH group will interact here and form this anomeric OH group. Now this new anomeric OH group can be on the top or at the bottom. So when it is on the top, that is your beta. When it is down, it is alpha, like just like glucose and rest of the carbon OH group. So the difference between glucose and galactose, you have to remember only in terms of C4. In C4, glucose it is down, and galactose, this OH group is up. That is the difference. So that way you should remember, and it is very simple to manage this carbohydrate chemistry. And this is, and for chemistry student, for us, will be more interested in knowing the structure properly. Once you know the structure, other reactions and other things are very simple. They are not. The structure, you have to understand the structure properly. And in solution, you see here, in solution, this will be in equilibrium. Now you see this equilibrium with the other one. Now, but in solid state, it will exist in this ring form only, either alpha or beta or both. If you do just take out the solid, you will find it is a mixture of both alpha and beta. But once you dissolve alpha, it starts converting, a portion of this one will start converting into beta, and there will be an equilibrium that we have seen in case of glucose also. If you dissolve beta, you will get a mixture of alpha and beta. So that way, both are that what is called. So that is what is your galactose structure. I am not doing the elaboration of this structure. Already we have done it for glucose. It is the same as glucose. So anything asked from this structure, you should be in a position to answer that one. Now this is a very important topic. Glycosides. Glycosides. What are glycosides? Now you see, if you remember your reaction with, sorry, if I just write down here, pointer, and this is suppose point here. Okay. Now, you remember that alcohol react, suppose alcohol, not alcohol, say an aldehyde, C double bond O, H, reacting with an alcohol, suppose alcohol, it is, let us call it an R prime OH in presence of HCl. What we got? We got hemiacetal, right? RCOH. Then this becomes OR prime and H. So, and which is unstable, and this is your hemiacetal structure. This is hemiacetal. And this, it is also reversible. The process is reversible. But again, when you react with further, if you react with more alcohol, again R prime OH, HCl, what you get? This OH group, which is also called hemiacetal OH group, reacts with this alcohol, and this OH group will react to give us what? What it is called? OR prime. So this will be your prime. Sorry, this is C, OR prime, then again OR prime and H, right? So this is what is called acetal.
Acetal.
Okay. Now, when we have seen in our glucose structure, what we have seen? Our glucose structure exists as hemiacetal. because that aldehydic group and the alcoholic OH group are reacting to give you the hemiacetal. But the hemiacetal, that time it becomes a cyclic because it is part of the same molecule. It is formed within the same molecule. Now that hemiacetal, if you react further with another alcohol, external source, what it will react? It will react with this, which is called an anomeric OH group and this alcohol, not with other, because carbohydrate, what is the difference? It has got so many other OH groups, but it will not react with those OH groups. It will react with this because our molecule is already in this form, hemiacetal form. So second alcohol, any alcohol, when we react, it reacts with this. And we get an acetal. So what is the difference? In the carbohydrate chemistry, they get a different name. They are not called acetal. They are not called acetals. Rather, what is called carbohydrate chemistry, what we get here, they are called glycosides. The monosaccharides and oligosaccharide, means disaccharide mainly, having free anomeric OH group. That anomeric OH group should be free. When treated with alcohol, give the acetal equivalent of the sugar molecule, that means the carbohydrate, monosaccharide or disaccharide, known as glycosides. That is a very important phenomenon here, glycosides. And also termed as O-glycosides, means it is the bonding with the glycoside with alcohol, and the OC bond is there. But if you treat with amines, it will give N-glycosides. So both these forms of glycosides are important in biological system. There are many N-glycosides which are there and very physical, I mean, they are very important as a biomolecules. But we are not dealing with N-glycoside, we are mainly dealing with O-glycosides. So this is glycoside. And the carbohydrate chemistry, glycosides are very important, what is called type of molecules. Now, what is next written? The glycosides once formed remain in cyclic form of the molecule and do not convert to the open chain form. Okay, why it does not convert, we'll just see. Hence, lose its reducing property, because that reducing property is because of what? That OH group was anomeric OH group converted into that open chain aldehydic form. So that aldehyde was responsible for reduction, but here it is not converted into aldehyde anymore, because there is a methyl group or any other alkyl group is attached there to oxygen. So that methyl group is not migrating to the other carbon atom. So that migration is not possible. So it does not go to that aldehydic form. In other words, it does not go to the open chain form. But the reaction as such is reversible. Remember, reaction as such is reversible. But this HCl which is there, it is a catalytic quantity. It is not present in very large quantity. But once it is formed, the hemiacetal, the glucose structure, once it is formed, you take it out, it is stable. It does not. Now after that, okay, we are coming to that one later on. The glycoside involved in the reaction, the glycosides involved with anomeric carbon produce what is called? The glycoside involved reaction with anomeric carbon, the product form will be alpha glycoside, as glycosides are involved in the anomeric carbon is involved, but anomeric carbon we know that can exist as alpha and beta. So glycoside also we can have alpha glycoside and also beta glycosides. So that is the very, very important point that is there. We have to remember this. So from this, just come to the reaction. So now you see here, this is our alpha, because once it is in solution, you will be having. Where is that? Okay. Now, once it is in solution, it will have both beta and alpha converting to one another through this open chain form. After that, this is our hemiacetal structure, right? So this OH group is going to react this OH group as well as this OH group. So this my and it's not. Okay, this OH group. So these two OH groups are going to react, not other OH group, which react with methanol. So it is hemiacetal reacting to give you the acetal, but we don't call it acetal here. We call it a glycoside. And this glycoside is formed from glucose, so it is glucoside. And it is beta here, so it is beta O-methyl because it is with the oxygen here, oxygen. So it is O-methyl glycoside. And alpha O-methyl, alpha D actually, D also will be there. Well, okay, we didn't give. Glucopyranoside, that is also the name, the full name. Both here also, I am writing here both in one only simple like glucoside and here glucopyranoside. Once we write pyranoside, but that means it is a 6-member ring. That is already, that is a part of that. The name itself will tell that it is a 6-member ring. So this is what is your glycoside, important. So in case of fructose, it will be the similar thing, but in this case fructose, now you see, now onward, this is the anomeric carbon for fructose, right? Carbon number 2. We will not write now once, because when it is in solution, anomeric group can be there, OH group can be there in alpha position or in beta position. So we will not specify them, either top or bottom. Once it is in the top, OH group in the top, that is beta, OH group is on the bottom, that becomes alpha. We will not specify because both are there. If we specify only one, that means other is not there. So that way we will not do it. That is not correct. So when we write D fructose, do fructofuranose actually, D minus because it is laboratory, it is D minus fructofuranose. So that time when we write, it is. So OH group we are writing separately, OH and the other group is CH2. So this. When we react with methanol and HCl, HCl is acting as a catalyst here only. So we'll get both beta and alpha glucoside. Sorry, it is fructoside. Fructoside. So it is beta, what will be the name here? Beta methyl D fructofuranoside. So that is the proper name, fructofuranoside. That is the name that is given. And this one becomes alpha O-methyl D fructoside. We can call also simply fructoside or fructofuranoside. That is why I have written both of them. In one case I have written fructofuranoside, in another case I have written fructoside. Both names are used. And beta, once it is alpha, this comes on the down. So whenever a glycoside is formed, a glycoside will be either alpha form or beta form. So that way, so that means it must be an alpha glycoside or it can be a beta glycoside. So that way, so ultimately what is a glycoside? How it is formed? Simply a monosaccharide whose anomeric OH group is free. This is the free anomeric OH group. Just see here. This is your free anomeric. My pen does not. Oh, okay. This free anomeric OH group. That means this H is H is free. That means it is not substituted by anything else. Free anomeric OH group. Then you treat this one with alcohol. You get a glycoside. So that means glycoside monosaccharide reacting with a alcohol. So we get an O glycoside. If we react with amine, we get N glycosides. N glycosides we are not taking here. So that is, you can understand this is going to be the similar type of molecules. But one thing remember, once it is formed beta here, suppose we can separate alpha and beta glycosides. We can separate alpha and beta, keep them separate. Now, if we dissolve it in solution, it is not going to convert into alpha. A beta will remain beta. That means what? Is not converting itself to the open chain form. That means there will not be any aldehyde group. So what will happen? That aldehyde group, when it comes out, because in the open chain form, was responsible for the reduction. So we will not have any reduction. Also will not have any oxygen formation. Also, it will not react with NH2. That means all the properties associated with the aldehyde group will not be there. So that is why the second green line, green paragraph you just see, glycoside once formed remain in cyclic form of the molecule, do not convert to the open chain, hence lose its reducing properties and other related properties. That means all glycoside will be non-reducing in nature. So remember that point. Now, and this point is also important. Hydrolysis of glycosides. Hydrolysis of glycosides, this is also important. Once we hydrolyze glycosides, what happens? Let us see. Uh, it is just the opposite of the formation of glycoside. Glycosides are stable in solution, do not convert into either forms. That means alpha will remain alpha, beta will remain beta. And glycosides are hydrolyzed by acids, remember, either hydrolyzed by acid, also by enzymes. But what about enzymes? What about enzymes? Okay, we'll come to that one. But once we hydrolyze means what? We get the corresponding, the product of hydrolysis will be the corresponding sugar. That means for suppose from glucose we'll get back the glucose and the alcohol, sugar and the alcohol. But once we get the sugar, because that OH group is it will get back its OH group. Once it is OH group, that means it is going to give you both alpha and beta. Got my point? All right. You get both alpha and beta. You don't get only, suppose you start with, say here, in this case, suppose, you start with beta O-methyl glucoside. So what you get, this is the group which is getting hydrolyzed. You do the mechanism yourself, because this mechanism already you have done it in your other classes. Hydrolysis of water. Hydrolysis with water in presence of acid. So what you get? You get here this OH group. First of all, you can show that this is the OH group. We started with beta. First we get beta, but beta will not remain beta 100%. It will also get converted into alpha, because already we know in solution they are interconvertible. So we get both alpha and beta in the same proportion that we have found that used to be present, and alcohol. So this is your product. If we do the same thing with alpha, we get the same thing. But if we do with enzyme, what happens? Enzymes are very specific. Now here comes a problem, not problem, that is an advantage or disadvantage, you can say that an enzyme which hydrolyzes alpha glycosides do not hydrolyze beta glycoside. Remember that. That is why you see you cannot digest cellulose. You can digest starch. Because starch and cellulose, the difference is in the glycosidic bond. We'll come to that one later on. So because enzyme which is present in your system cannot hydrolyze the other glycoside, it can hydrolyze only the glycoside that present in starch. And starch and cellulose, that is the difference. You got my point here? Got the point? Just respond. Say yes or no.
Yes, sir.
Huh?
Yes, sir.
Okay. So we'll come to this this pointer. We erase everything. We go to the next slide. Anomeric effect. Okay, this is what is another very important phenomenon. Anomeric effect. And in this regard, I have given one question to you. Only 4 of you have submitted. That is roll number 20, roll number 09, 53, and 42. 4 people. Of course, I did not insist that you should submit, because that is not a regular question. I thought, okay, those who can submit, all right. Those who, but all of you, did you try it? What was the question?
Yes.
Question was, first question is, why in solution beta glucose is present in higher percentage, 64% compared to alpha glucose? That was the first question. Already we have seen it through that meter rotation phenomenon of meter rotation. We have already proved that alpha glucose is present to the extent of 36% and beta glucose is present to the extent of 64%. Almost. It's not that exactly that figure, but it's almost close to that. That is, and it is a natural phenomenon. If you put only alpha glucose on solution, they will adjust to this figure. Become this mixture of alpha and beta. Now the question is why it is happening that way? Why beta glucose is present in higher percentage, 64%, but alpha glucose is present in lower percentage, only 36%. Can somebody explain this? I got the answer. Probably you have also, you know the answer by now. If you have just little bit studied this one. Yes, somebody tell. I find the name.
Yes, sir.
Okay, tell me.
Beta T glucose is OH group is axial position. That
Hmm.
means equatorial position. That
Yes.
means equatorial position is more stable than axial position. Then therefore, sir, beta D glucose is present in higher percentage compared
Oh,
to alpha
okay,
glucose.
okay. This is true. Axial position is more stable than, sorry, equatorial position is more stable than axial. This is true only when your a simple group is there. But here it is an OH group. An OH group is not that only H is there. The oxygen is also having a lone pair of electrons. That also has got an impact. Your answer is correct, partially correct, not fully correct. Okay, you are partially correct
Yes.
because what is happening here? Come to the second part of the question. But when methyl glucoside is formed, is prepared from glucose, you just prepare glucoside from glucose by treating with methanol. After that, when you isolate this, because it will be both alpha glucoside and also beta glucoside. Now in the mixture, what you will find, alpha glucoside is found to be present in higher concentration, just the opposite. It is 66% and beta is 33%. What has happened? Now you cannot say that because beta is beta, a bulky group will be present in equatorial. Beta group, OH group is also in equatorial. Beta O methyl group is also in equatorial position. But here that logic does not hold good. You just see the opposite phenomenon. This is because this is an effect which is called anomeric effect. This term is there. This is the anomeric effect. You just see on the top written there, anomeric effect. This phenomenon is called anomeric effect because it is happening with the anomeric carbon atom and anomeric OH group. Now this is, you see here, beta glucose is present because this OH group which is there is OH group is present in the equatorial. This is one aspect. But this two lone pair of electron, this two lone pair is also there. These two lone pair of electrons are also there. But these two lone pair take this direction, does not go this side, because this hydrogen atom gets hydrogen bonded to this oxygen. Through this lone pair, of course, this writing is not very correct. This notation is not very correct. It should be through lone pair of electron. It comes here, lone pair oxygen and this hydrogen. So it becomes that way it is. But when it is alpha, it is not possible. Just see, when it is alpha, this OH group is quite far. This OH group hydrogen bonding is not possible there. This OH group is quite far from this lone pair of oxygen. So that is not possible. So it does not have that hydrogens. So this is why this beta is present in higher percentage. But when you do So this is more stable because of this hydrogen bonding. Now, if we go to the glycosides, if you prepare now glycoside, so this H becomes replaced by methyl group. Once H gets replaced by methyl group, then this oxygen and this methyl group will not have any interaction. So rather methyl group will come this side and this lone pair of electron will go that side. And these two lone pair, they will have interaction here. They will have an interaction. So this interaction is going to make this one unstable. Whereas in the alpha position, when we go to the alpha methyl glucoside, we find that this is present, comfortably present, far away from this lone pair and this lone pair. So that is the reason why this is going to be alpha methyl glucoside will be more stable than alpha methyl glycoside. Now, now this anomeric effect we are seeing here in this what is called this case of carbohydrate. But anomeric effect will be observed only when there is an heteroatom here on this is a heteroatom, and also an heteroatom here on the first adjacent carbon atom. There is an heteroatom. So there are many other substances, even it may be chlorine, it may be sulfur, it may be any other. So it is a general phenomenon. This effect is called anomeric effect. Now I'll be forwarding you one note, actually one complete article on anomeric effect. Anomeric effect having different type of structures. How this one changes with the structure, the percentage will vary because of these different groups present. In the PDF format, I'll separately give you. Those who are interested to learn more about the anomeric effect, you go through that one. Also, that may be interested, for NAT and GATE examination, that will be important. That type of phenomenon. So you will go through that one, and for simple understanding, suppose you don't want to take that consideration, okay, this is what is there for this. So this anomeric effect is a very important phenomenon. Remember that. We have to end up our class quite now. Okay, now quickly, disaccharides will start in the next class, but quickly let us see now disaccharide. Once you have understood what is a glycoside, and you know what is an alpha glycoside and what is a beta glycoside, your disaccharide is complete, more or less. You know, once you know monosaccharide chemistry properly, your disaccharide is nothing but a little extension of monosaccharide. Now, three important disaccharide. One is maltose. You know that one. One is maltose, one is sucrose, one is lactose. What is disaccharide means what? They on hydrolysis will give you two monosaccharide. Maltose gives you glucose plus glucose. Sucrose will give you glucose and fructose, and lactose will give you glucose and galactose. What question come to your mind? Can anybody tell what is the question that will come to your mind? Any question? Now here, because as a student of chemistry, all of us should be interested more in their structure, not other things. Other things will follow. Reactions and all will be because of their structure. So what question come to your mind? Can anybody tell? Any question does it come to your mind about their structure?
Sir, that glucose and fructose here in here, it is alpha or beta? That one.
Any other question?
And in which position the glycosidic bond is? It is in 1,2 position or 1,4 position, like this.
The first question that should come to how these two are connected. This here we find that it is maltose. It is 2 glucose. In sucrose it is glucose and galactose, fructose, and lactose it is glucose and galactose. The first question that should come to your mind, how they are connected. Because there are so many carbon atoms, there are 6 carbon atoms here and 6 carbon atoms here in all the cases. Which one is connected? Which carbon atom of one glucose is connected to which carbon atom of second one? And so also in all of them. Now, what should be the natural connection? Natural connection. By now you should know what from which carbon atom they should be connected, and through what type of bonding. What is your natural answer to that one? I think we have to end our class quickly because two things. One will be your Ganguly sir will be waiting for the class. Another second is that we have to leave this Zoom platform for your Nicholas sir because he is going to take a net class on using the same. Anyway, come on, quick. Daisy,
Sir,
what will be the natural way how they should be connected? Already we know the phenomenon.
so by glycosidic bond.
They should be connected through glycosidic bond. Because what will happen here, one of this monosaccharide, any one, maybe glucose, fructose, we don't know. We have to see that one. Will connect with the second monosaccharide. When the first monosaccharide will act, it will act through its anomeric OH group, and the second one will act as an alcohol. That means it is going to form a glycoside. Structurally, disaccharides are glycosides of monosaccharide. You see here, glycosides are monosaccharides. And so therefore, once it has glycosidic bond, means disaccharide is formed by condensation of one monosaccharide through one specific, that means specific when we say alpha or beta anomeric OH group with the one particular OH of the second monosaccharide. So the second monosaccharide will act as an alcohol. So it is formation of glycoside. One monosaccharide will act as a monosaccharide, means as a sugar molecule. The other monosaccharide will act as an alcohol. So it is a reaction between the monosaccharide and an alcohol. The second molecule of monosaccharide will be acting as an alcohol. Now, bond involved in the glycoside formation is also known as glycosidic bond. Already we have done that one, we know that. And then, let me not extend this one. We'll come to this one later on. And this is what is our structure. And then first, so our main thing will be that how they are connected. So in case of maltose, we find that glucose C1 can be short way we can learn this. How the linkage is that C1 of one glucose is linked to the C4 of the second glucose. The C1, that means the anomeric OH group. Once it is anomeric OH group, which way it is connected? It is through alpha. So that is what is the short form of maltose. And the C4 of the second. So C4 OH group will be acting as an alcohol. As a result, what happens in this maltose structure, the C1 is going to remain as free OH group. Once it is free OH group, that means that anomeric OH group means what? It will also become aldehydic group, become open chain form. Open chain form, once it is open chain form, it will have reaction of aldehyde, mutual rotation, all this phenomena. But when it is coming to sucrose, it is the C1 of this sucrose will react with the C2 of the fructose. C1 is also the anomeric OH group here. The second one is also anomeric OH group. So both anomeric OH group are condensing with one another. So they are glycosides of each other. We'll take that one later on. And here it is galactose. Galactose C1 is reacting with the C4 of glucose. So this glucose unit, the C4 C1 is free. So with this, I finish this class. You will end the show. Discard this. And okay, we come back. come back to our normal. Stop share. So, okay. I think you go through this. If my recording is fine, we'll see this. I'll send you this. But when I see my other uh, YouTube channel, I find only the first video is watched by large number, but other videos are not properly seen. The number is very less. Okay, whenever you have doubt, you can go through this one. Not that you have to always, because once you start listening, you should listen it carefully. At the same time, you should uh, it takes time, so you should not always see this one, and read it and also practice. So only little bit of practice will make you expert in carbohydrate chemistry. I'm telling you, you become expert. So let us end this class. Okay, all the best. We'll do our class next on Friday. We'll start with the
Thank you,
disaccharides.
sir.
Okay,
Okay, sir. Thank you, sir.
all right. Goodbye. Huh? Stay well.